In this pod, we'll look at how you determine the half-life of a model radioactive source.
When thinking about radioactivity, we first need to think about and understand the structure of the atom. Atoms contain three types of subatomic particles. These are electrons, protons, and neutrons. The nucleus of the atom is found in the center of an atom and is very small. The nucleus contains the protons and the neutrons. The number of protons gives the atom its atomic number and determines which element it is. The number of protons plus the number of neutrons is the atomic mass of the element. Electrons exist in different energy levels and are found around the nucleus.
You can draw this as a collection of circles. The nucleus is a very small circle in the center of your diagram. The electrons are positioned on larger outer circles. If an atom has 5 protons, then it will also have 5 electrons. This means it is an atom of boron.
For a particular element, the number of neutrons in the nucleus can vary, but the number of protons stays constant. Remember that if an atom has a different number of protons, then it is an atom of a different element. Atoms of the same element that have different number of neutrons are called isotopes of that element.
Now we can turn to radioactive decay. The nuclei of some isotopes are unstable. They can split up or decay and release radiation. Such isotopes are called radioactive isotopes or radioisotopes. When a radioactive isotope decays, it forms a different atom with a different number of protons.
Atoms of these radioactive isotopes can give off radiation because they are unstable. They either emit alpha particles or they emit beta particles. You need to know that an alpha particle consists of 2 protons and 2 neutrons. It is a helium nucleus.
We can write equations to represent radioactive decay. This type of equation gives the atomic number, the atomic mass, and the chemical symbol of the initial radioactive element, as well as of the new element that is formed. You will find this next stage much easier to follow if you either look at the image on the screen or write this down on some paper.
Let's look at an example of alpha decay first. Uranium is unstable and decays to thorium by giving off an alpha particle. First, consider the chemical symbols. Uranium, symbol U, forms thorium, symbol Th, and an alpha particle, symbol He. Now consider the atomic mass numbers. You write these at the top left of the chemical symbols. Uranium is 230. Thorium is 226, and helium is 4. Finally, consider the atomic numbers, which is the number of protons. You write these at the bottom left of the chemical symbols. Uranium is 92, thorium is 90, and helium is 2.
Did you notice that the numbers balance? 230 equals 226 plus 4. 92 is 90 plus 2. Now let's look at an example of beta decay. A beta particle is emitted when a neutron in the nucleus gives off an electron and so changes into a proton.
An example of beta decay is when carbon-14 decays to form nitrogen by emitting a beta particle. A beta particle is a high-energy electron. The chemical symbols are C forms N and E. Next, we have the atomic mass numbers. The mass of carbon-14 is 14. It forms nitrogen-14 plus 0 for the electron. Electrons have negligible mass, which is considered to be 0. Finally, let's look at the atomic numbers. Carbon is 6, nitrogen is 7, and the atomic number of a beta particle is -1. This -1 is needed to balance the number of protons.
During radioactive decay, the atoms which will decay are completely random. What we do know is that half the undecayed nuclei will decay in a time that is known as the half-life of the isotope. This is best explained by an example. If the half-life of an isotope is 40 years, then half the nuclei will have decayed in 40 years. That is, 50% of the original total will have decayed. Over another 40 years, a further 25% of the original atoms have decayed, so a total of 75% have decayed and 25% of the original atoms remain.
The curve starts where the time equals 0 on the x-axis and the number of undecayed nuclei equals 100% on the y-axis. After one half-life, the number of undecayed nuclei equals 50%. After another half-life, the number of undecayed nuclei equals 25%. Subsequent half-lives see the number of undecayed nuclei fall to 12.5%, 6.25%, and so on. You'll see a curve that declines steeply at first and gradually becomes less and less steep.
You can model this by using dice. Let's say you use 100 dice. You would put them into a shaker and then tip them onto the bench. In this model, all the dice which landed showing a 6 represent atoms that have decayed. These are counted and removed. You also need to count the number of dice remaining. Now put all the dice that didn't show a 6 back into your shaker and tip them out again. This is repeated over several throws. Enter your results into a table. This table could have the following columns: roll number, number of 6s removed, which is the number of decayed nuclei, and the number of dice remaining, which is the number of undecayed nuclei.
Some sample results could be: before you start, roll 0, 0 6s, all 100 dice remain. Roll 1, 17 6s, 83 dice remain. Roll 2, 14 6s, 69 remain. Roll 3, 11 6s, 58 remain. Roll 4, 9 6s, 49 remain. Roll 5, 8 6s, 41 remain. Roll 6, 7 6s, 34 remain. Roll 7, 5 6s, 29 remain. Keep going until you have no dice left.
You can now plot a graph. Put the number of the throw on the x-axis and the number of remaining dice on the y-axis. What shape of curve does this give you?
You could repeat the experiment and this time remove more dice each time, perhaps removing all the dice showing a 5 or a 6. This will give a curve that drops off more sharply. This is similar to the decay curve of an element with a shorter half-life.